In this screencast, I am going to demonstrate a process for integration by trig substitution that uses trigonometry to evaluate integrals that don't appear to have anything to do with trigonometry. Here's the situation. My parents went away on a week's vacation. No, it's an old song. So sorry. So sorry. Let's pretend that our integral has x squared plus a number in it, or maybe x squared minus a number in it, or maybe a number minus x squared in it. And the solution, the technique, is going to be that we're going to build a right triangle and get triggy with it. Please allow me to demonstrate. Let's pretend that we're going to find the integral of the square root of 1 minus x squared dx. It seems straightforward enough. And for us, we don't have another way to do this. U substitution doesn't work because the derivative of 1 minus x squared has a negative 2x in it. That's nowhere to be found. We don't have another way at this. We are stuck. So what do? I will outline a 4-step process. Step 1. Let's build a right triangle. What does that right triangle look like? Well, that right triangle is going to have as one of its sides square root of 1 minus x squared. Now, that can't be the hypotenuse because it's got a minus in there. So it's one of the legs, and it really doesn't matter which one. The other two legs are the square roots of these numbers. Why? Because Pythagorean theorem says that this squared plus this squared has to be this squared. So this squared is that squared minus that squared. So the square roots of the 1 and the x squared occupy the other two sides. We're going to label this angle theta, and we're going to use it. Step 2. We're going to sub for every expression involving x. Every one. So how do we do that? We do that by establishing some relationships over here. We establish the relationship between the linear term and the constant term, and we evaluate the relationship between the radical and the constant term. Well, x over 1, linear over constant, that's adjacent over hypotenuse, that's cosine theta. The radical over 1, that's opposite over hypotenuse, that's sine theta. Why do we do this? Well, we've got to make a substitution for the radical, so we've got to have something that is the radical. But we also have to substitute for a dx. So we need to know what x is so we could know what dx is. X is 1 times cosine theta. So dx is negative sine theta. And we make the substitutions. The radical, that's sine theta. Dx, that's negative sine theta d theta. That's everything there is. If there were limits on the integral, we would figure out what those limits are in terms of theta and substitute them in. This is negative integral sine squared theta d theta. Step 3. step 3 is to evaluate the integral. Well, we just did how to evaluate integrals like that. We substitute a double angle. That's a double angle. And I know how to do that. Let's break this up into two parts. This is a 1/2, and this is a 1/2 cosine 2 theta d theta. So this is negative 1/2 theta plus 1/4 sine of 2 theta plus a constant. That's how we evaluate the integral. Well, time to substitute back. And this is where things get a little bit tricky. What's theta? Well, theta is this angle here. Can't divide by cosine, but we can think about theta as the angle whose cosine is x over 1. Theta is the angle whose cosine is x over 1. Then we got to think about sine 2 theta. Well, sine 2 theta is 2 sine theta cosine theta, said my trigonometry teacher. Sine theta, we know, and cosine theta, we know, plus a constant. We use trigonometry to figure out something that has a radical in it where that radical could be the side of a right triangle. So recapping, we build a right triangle, one of whose sides is the radical expression in our problem. We substitute for every expression with an x in it. We evaluate the integral, which is why this lesson had to follow the last one, and then we substitute back. I'm going to do another screencast that's going to do 2 more examples if those would be helpful to you. Hope this is a good start.